Okay, here's your Chapter 7 review sheet. If we have to simplify the square root of 48, we want to think of factors of 48 that are perfect square numbers. So I think of the square root of 16 times the square root of 3, because 16 times 3 is 48. The square root of 16 is 4, so simplified we get 4 times the square root of 3. To simplify 3 times the square root of 50, I'm going to break up 50 into the square root of 25 times the square root of 2. Then I'll have 3 times 5 times the square root of 2. 3 times 5 we can multiply and we get 15 times the square root of 2. The next example, we cannot leave a radical in the denominator, so I'm going to multiply numerator and denominator by the square root of 5, because when I do that, my denominator is going to become the square root of 25, which is 5. So I have 12 times the square root of 5 over the square root of 25, which is 12 times the square root of 5 over 5. Next question we have, find the geometric mean between 2 and 6. We know that the definition of a geometric mean is the square root of the product of two numbers. So I can set this up as the geometric mean is x between 2 and 6. When we cross multiply, we get x squared is equal to 12. X is equal to the square root of 12, which can be broken up into the square root of 4 times the square root of 3. And that simplifies to 2 times the square root of 3. So the geometric mean between 2 and 6 is 2 times the square root of 3. Next example, we have an altitude drawn to the hypotenuse of a right triangle. We know that we have similar triangles formed here, and we also end up with 3 things that are geometric means. Each leg is a geometric mean of the large triangle, and the altitude is a geometric mean. So we can start with any one, but I'll start with y. Y is the geometric mean between the segments on the hypotenuse, 3 and 12. So y squared is equal to 36, y equals 6. At this point, you could use a Pythagorean theorem if you want, or you can set up using geometric mean again, because x is the geometric mean between 3 and the whole hypotenuse, 15. So then x squared is equal to 45. X equals the square root of 45, which can be simplified into the square root of 9 times the square root of 5, which is 3 times the square root of 5. So x is equal to 3 times the square root of 5. Then for z, we have z is also a geometric mean between the whole hypotenuse, 15, and the segment of the hypotenuse that's adjacent, which would be this 12. So then when we cross multiply here, we get z squared is equal to 180. And then you want to think to yourself, what are some factors of 180 that are perfect square numbers? So I can plug into my calculator 180, divide by 4, and I get 45. Well, I know 9 is a factor of 45, so I'm going to try a larger number, 180 divided by 36, and that is 5. So I'll break up 180 into the square root of 36 times the square root of 5. And so z is equal to 6 times the square root of 5. So we get 6 times the square root of 5. Next example. Here we have 6 and x are both geometric means, so let's start with the 6. 6 is the geometric mean between the whole hypotenuse, 12, and the segment of the hypotenuse that's adjacent, that would be y. So then we cross multiply here, we get 12y is equal to 36. Y is equal to 36 divided by 12, which is 3. So this piece right here is 3, which means that from here to here would have to equal 9, because 3 plus 9 gives us the 12. So then x, which is the altitude drawn to the hypotenuse of this right triangle, x is the geometric mean between the segments on the hypotenuse being 3 and 9. So cross multiplying, we get x squared is equal to 27. X is equal to the square root of 27, which is, square root of 9 times the square root of 3, which is 3 times the square root of 3. So x is 3 times the square root of 3. Next, we're using the Pythagorean theorem. The Pythagorean theorem says that the sum of the squares of the legs is equal to the square of the hypotenuse. So I have x squared plus 15 squared is equal to 17 squared. So then x squared plus 225 is equal to 289. Remember, we memorized our squares up to 20, so then I have x squared is equal to 289 minus 225, which works out to be 64. So then x is equal to the square root of 64, which is 8. Next example, we're looking for the hypotenuse, so I have x squared is equal to 2 times the square root of 3 squared plus 8 squared. So then x squared is equal to 2 root 3, here we'll think over here, 2 times the square root of 3 times 2 times the square root of 3. So we multiply the whole number portion, we get 4. And then the square root of 3 times the square root of 3 gives us the square root of 9, which is actually 3. So this is 12 plus 64. X squared is equal to 76. X is equal to the square root of 76. So we have to simplify that. So we're going to think, what are some factors of 76 that are perfect square numbers? And so 76 is actually divisible by 4, and that works out to be 19. So we have the square root of 4 times the square root of 19. So simplified, x is equal to 2 times the square root of 19. 2 times the square root of 19. Next, we're looking for one of the legs. So we can write x squared plus the square root of 12 squared is equal to 6 squared. So x squared plus the square root of 12 times the square root of 12 is actually 12, because you actually get the square root of 144, which we know is 12, and that's equal to 36. So then we're going to subtract 12 from both sides, and we get x squared is equal to 24. X is equal to the square root of 24. So we break that up into the square root of 4 times the square root of 6, and we get x is equal to 2 times the square root of 6. Okay, that's page 1. Next part of our review is we're going to use the converse of the Pythagorean theorem. Converse of the Pythagorean theorem says if the longest side squared is less than the sum of the squares of the other two sides, then we have an acute triangle. If the longest side squared is greater than, we have an obtuse triangle. And if it's equal to, then we have a right triangle. So what type of triangle has the sides 7, 7, and 9? Well, we first know it is isosceles. But then I want to know what kind of isosceles triangle is it. So we're going to check to see, how does 9 squared compare to 7 squared plus 7 squared? Well, 9 squared is 81. So how does 81 compare to 49 plus 49? It's actually smaller, so therefore this is an isosceles acute triangle. Next we have the special right triangles. The 45, 45, 90. We know that the legs are equal, so I'm going to do my reference triangle first, so I have that to look at when I'm solving the other two. The hypotenuse is going to be x times the square root of 2. Excuse me. Then in the 30, 60, 90, if the smallest side is x, the hypotenuse is 2x, and the longer leg is going to be x times the square root of 3. Okay, so that's our reference triangle. Let's go back to the 45, 45, 90. Here the legs are both going to be equal, so that side is equal to 8. Matching it up, this side is going to be 8 times the square root of 2. This next example, I have the hypotenuse is 40. Well, looking at the reference triangle, 40 is actually equal to x times the square root of 2. So I'm going to set up an equation. 40 is equal to x times the square root of 2. So I can decide, okay, what do I need to do to figure out what my leg is? Well, I have to divide this by the square root of 2. So x is equal to 40 divided by the square root of 2. We can't leave a radical in the denominator, so I'm going to multiply numerator and denominator by the square root of 2 over the square root of 2. Because we can always multiply something by 1 and just change its appearance, not its value. So then here, we'll now have 40 times the square root of 2 over 2, which can be simplified to 20 times the square root of 2. So each leg is 20 times the square root of 2. Now on to the 30, 60, 90. In this first example, I'm given the side opposite the 30-degree angle, which is the shortest side, which in the reference triangle, the shortest side is x. The longer leg is going to be x times the square root of 3. So here, instead of x, I'm going to have 10, actually. So we have 10 times the square root of 3. My hypotenuse is going to be double the short leg, so it's going to be 2x, 2 times 10. Next example, I have the longer leg, but there's no square root of 3 visible, so looking at the reference triangle, 6 is equal to the leg times the square root of 3. So we have to solve for the shortest leg, so I'm going to divide both sides by the square root of 3. Can't leave that radical in the denominator, so I'm going to multiply both numerator and denominator by the square root of 3 over 3. Square root of 3 over the square root of 3, so I get 6 times the square root of 3 over 3, which reduces to 2 times the square root of 3. So that means that my short leg is 2 times the square root of 3. For the hypotenuse, we're just going to double that, and we're going to get 4 times the square root of 3. And that's the basics of the 30, 60, 90. For the tangent, sine, and cosine portion, we're going to write up here, the old aunt sat on her coat and hat. So we see what our ratios are for the tangent, opposite over adjacent, sine, opposite over hypotenuse, and cosine, adjacent over hypotenuse. So the first example, we're using our 32-degree angle here. The 5 is the opposite, x is the adjacent, so that tells us we're going to have to use the tangent of 32 degrees is equal to the opposite, which is 5, over the adjacent, which is x. When we cross multiply, we have x is equal to the tangent of 32, or x times the tangent of 32 is equal to 5 times 1, which is 5. So then we're going to have to divide both sides by the tangent of 32. So we have 5 is equal, or x is equal to 5 divided by the tangent of 32. So then we're going to plug that into our calculator. 5 divided by tan 32. I'm going to close my parenthesis just for good habit. And we get 8. So x is equal to 8. Next example, we have to be given a little bit more information here, so I'll say that those two lines are parallel. So in that case, we know that alternate interior angles are equal, so that's 50. And because, let's see, in order to get x, I'm going to need more information. So I'm going to have to find the length of this line right here in order to help me find x. So let's call this y. So then what function am I going to need? Well, if I use this 50-degree angle, the 6 would be the opposite side, y would be the hypotenuse. So which one of my functions deals with opposite and hypotenuse? It's that sine. So we're going to take the sine of 50 degrees is equal to the opposite side 6 over the hypotenuse, which is y. Put that over 1 when we cross multiply, we have y times the sine of 50 is equal to 6 times 1, or 6. To solve for y, we're going to have to divide both sides by the sine of 50. So y is equal to 6 divided by the sine of 50. So into our calculator, 6 divided by sine 50. I'm going to end my parenthesis there. And we get 7.8. So this piece is 7.8. So I'm not finished yet because now I have to use this information to help me solve for that x. So what function, if I'm using this 50-degree angle, the 7.8 is the adjacent side, x is the hypotenuse. So adjacent and hypotenuse is our cosine function, so we're going to say cosine of 50 degrees is equal to the adjacent 7.8 divided by the hypotenuse x. Cross multiplying, we get x times the cosine of 50 is equal to 7.8. Divide both sides by cosine of 50, so we get x is equal to 7.8 divided by the cosine of 50. Plug that into our calculators. 7.8 divided by cosine 50, and we get 12. X is equal to 12.1. On the test tomorrow, we're just going to make sure that we read the directions and see if we want it to the nearest tenths or the nearest hundredths place. Next example, we're looking for the angle. So we're going to set up using our functions the same way. We first think, what function do we need? 10 is the opposite from the angle,